Hi everybody. So I wanted to do a little bit of cleanup of the 2D kinematics lecture. I was able to get most of the way through it during our live sessions, but because I'm trying to catch up a little bit and I want to spend a lot of time on Newton's laws and F equals ma, I wanted to kind of record this small kind of cleanup of that lecture, and then we can start fresh in class. So I'm going to go back to the 2D kinematics lecture and just cover the stuff at the end of the lecture, things which I did not cover in class. So a good place to start, if I go, is maybe with these clicker questions. So we had talked about the x and y dimensions, or the x and y axes, as being independent when it comes to projectile motion. So for example, if you throw something, it's going to form a parabolic shape throughout its trajectory. And if you look at it, you see that the x velocity here never changes. And that's because there's no force in the x direction. So the x velocity never changes. But the y velocity is changing because the acceleration due to gravity is in this direction, downward. Okay. So what I wanted to do was, let's start with a couple of clicker questions. So here's one. Projectile 1 and 2 are launched over level ground with the same speed, but at different angles. Which one hits the ground first? So projectile 1, projectile 2, same time, or there's not enough information to tell. Go ahead and pause the video and see if you can wager a guess. Think about your best guess as to which one of these hits the ground first. Okay, so hopefully you have chosen one of these answers and you have committed to one of those answers. The answer is that the first one that hit the ground is projectile 2. And the reason is you have to ignore what's going on in the x direction. Okay, so remember, the x direction is independent of the y direction. What controls how long the thing stays in the air is how fast it's thrown in the y direction. Okay. So in other words, if I kind of look at just the projection of this thing onto the y-axis, I would see that ball 1 is launched up. Imagine throwing it straight up. It goes up to here and then comes back down. And ball number 2 would only go up to here and come back down. So if you launch them both at the same time, it's pretty clear that the one that you throw higher, the one that you throw with an initial y velocity, which is bigger, will hit the ground later than the one that you launched with the lower y velocity. And if you don't believe me, you can go and play with this. There's a simulation posted on D2L in the links and resources section, and you can adjust the initial angle and the speed, and you can time how long it takes for it to go. Okay, so this is our D2L shell. I'm in the links, videos and links section at the very bottom. And there's this thing called Projectile Motion Study Applet. So I'm clicking on that and opening it up. And we're going to have to open it in a new window. Okay. So as I wait for this thing to load, I think this is good. So we'll go to the lab part of it. All right, so you have a cannon here. You can change the angle and you can launch it with different speeds. So let's take the initial speed to be 18 meters per second. And I'm going to launch it. Here we go. And you will also be able to time how long it takes. So here we go, like this. Okay. And notice here, I think I can calculate the time by looking at this thing will tell me the time and how far it's gone and how high it's gone. So going to the very bottom here, it hit the ground after 3.6 seconds. Okay. And this is how far it went, and that was this is the final height. Now let's launch another one. So let's launch another one at a very shallow angle, like this. And let's measure the time that took. It hit the ground after 1.55 seconds. So the first one was 3.6 seconds. The second one, 1.55 seconds. You can see what controls the time that it takes to hit the ground is the y velocity. And of course, the one at the sharper angle has an initial y velocity which is higher, and so it spends more time in the air. Okay. All right. Follow-up question. These two reach the same height, projectiles 1 and 2. Which one hits the ground first? Go ahead and pause the video, see if you can commit to one of these answers. So hopefully you've paused the video, you've guessed one of these answers, or at least wagered your own opinion. Hopefully from the example on the previous slide, you realize that these will hit the ground at the same time, because they have, if I look at the motion in the y direction, both of those two are going to the same height, and so they will in fact hit the ground at the same time. Maybe I can ask a follow-up question. Which of those two is launched with a greater initial speed? So they have the same speed or they have different speeds? You can see because they go to the same height, they have the same initial y velocity, right? Because the y direction is what controls how high it goes. But number 2 went further, and that means that it had a greater x velocity to start. So they have the magnitude of the speed v1 is going to be smaller than the magnitude of the velocity v2, because v1y is equal to v2y, but v1x is less than v2x. The x velocity is what controls how far it goes in the x direction. The y velocity controls how far it goes in the y direction. Okay, this is the example which I solved in class about dropping a package and figuring out where it hits. So that is in the previous recording. And I've got another clicker question here, which is about, the classic example involved shooting a monkey. So imagine you're hunting, and no monkeys are harmed in the making of this lecture. Imagine you're trying to shoot the monkey with a blow dart. Maybe you're a scientist, okay? You're not hunting the monkey. You're a scientist. You want to sedate the monkey so you can study it, okay? That's fine. So you're trying to shoot the monkey with a blow dart. The monkey is holding onto a vine directly in front of you at the same height as the dart. And at the exact instant you let the dart go, the monkey notices and lets go of the vine. The question is, where should you aim to hit the monkey? Should you aim directly at it, above it, or below it? And you can ignore the fact that the monkey has some size, so just treat it like a point. The height of the dart and the height of that monkey are exactly at the same height. Do you aim above, below, or directly at the monkey? And as usual, we're ignoring air resistance in this case. Go ahead, pause the video, see if you can answer this question. So hopefully you've paused the video and you've voted or wagered a guess what you think here. The answer is that you should aim directly at the monkey, believe it or not, because both the dart and the monkey are affected by gravity in the same way. They both fall at the same rate. Remember that gravity affects all objects the same regardless of their mass. They both have an acceleration equal to g downwards. And so if you aim directly at the monkey, your dart will fall at the same rate that the monkey is falling, and you will hit the monkey. Here's a more complicated example, which is now the monkey is at some angle. Okay, so let's suppose you're some distance away, and so the monkey's above you in a tree. The same situation. You're going to send the blow dart. And the minute that you let go of the blow dart, the monkey's going to let go. Do you aim directly at the monkey, below it, or above it in order to hit it? So this question here is giving you some numbers. So let's say the monkey's holding onto a vine 50 meters horizontally ahead of you, 40 meters above you. And then the speed of your dart is 100 meters a second. Show that if you aim directly at the monkey, the dart will hit it. So the answer to this one is also directly at the monkey. And we're going to show that that's the case. All right, so we've got a nice picture here. Let's just try to make it a little more explicit. My dart is going to be launched from this height here with some speed vi, like this. And let me pick a coordinate system now. So I'm going to pick this direction to be x and this direction to be y. So this will be y, this will be x. And the monkey is here. So there's going to be the distance between the initial position of the dart and the monkey, let's call it d, and let's call the height here of the monkey h. So we know that the dart is going to be launched with this velocity. So it'll go up like this, but then it will curve down, right, because of gravity, and eventually it will be somewhere there when it reaches the position of the monkey. Now the question we want to ask is, after the dart has traveled a distance d, d is 50 meters, h is 40 meters, where is it vertically, and then where's the monkey at that time? All right. This angle here, let's call it theta, and that angle is the same angle as the triangle formed by D and H, right? So I've got a triangle which looks kind of like this. This is H, and this is D, and this is theta. And the initial velocity is in that direction because I'm aiming directly at the monkey, VI, like that. Okay. Using this, you can figure out that angle. Tangent theta is h over d, which is 40 meters over 50 meters. And from this, you can find the angle. It's 38.66 degrees. Okay. Now, let's try to write down equations for the dart and for the monkey. Picking my origin to be at the position of the dart. So let's write down the equations for the dart and for the monkey. So monkey's equations, here we go. So I'm going to call it x for the monkey of t. Well, the monkey is always at the position d, right? It doesn't change in the x direction, it only moves in the y direction. So that is fixed. What's the y position for the monkey? It falls under gravity. So I have yi for the monkey plus viy for the monkey times t minus 1/2 g t squared. The initial position for the monkey is h. There is no initial velocity because he just drops. He just lets go of the vine. So he has no initial velocity. Minus 1/2 gt squared. Okay. Let's write down the equations for the dart. Maybe I'll do it up here. The dart equations. X for the dart. It's projectile motion, so it travels some velocity vix times t plus xi for the dart. And the initial position of the dart is 0 because I chose it to be 0 at the center of my coordinate system. Okay. And then what is the y position for the dart? It's yi for the dart plus viy for the dart times t minus 1/2 gt squared. And yi for the dart is also 0. Okay, so we have everything out mathematically now. What's our plan? First thing I'm going to do is I'm going to find the time it takes for the dart to travel a distance d. It was 50 meters. Then I'm going to find the height of the dart at that time. And finally, I'm going to find the height of the monkey at that time. Okay, so let's do that. go to a clean slide. All right, so step 1. To find the time it takes the dart to travel a distance d, I'm going to use equation for the x, this x equation up here. So I'm going to use this equation. So the position of the dart is going to be d, and then it's going to be vi, the x component of the velocity, times t. So xi for the dart of t is vix for the dart times t. And that's the x component of the velocity. So vi times the cosine of theta times t. Okay. So I'm going to have here the distance that it travels is going to be vi times the cosine of theta times t. So t, the time that it takes the dart to travel 50 meters, is d divided by vi cosine of theta. And plug in the numbers here. D is 50 meters, 100 meters per second, cosine of 38.66 degrees. And I got 0.6403 seconds. So a little bit more than half a second for the dart to travel in the x direction 50 meters. Step 2. What is the y position of the dart at that time? So step 2 is find the height of the dart at that time. So now I'm going to use the y position for the dart. And sorry, I think I screwed this up. There shouldn't be I there. This is just the position of the dart, not initial position of the dart. Y position of the dart as a function of time. VIY for the dart times t minus 1/2 gt squared. The initial y velocity is magnitude of v times the sine of theta times t minus 1/2 gt squared. Plug in the numbers. 100 meters per second, sine of 38.66 degrees times 0.6403 seconds minus 1/2 times g is a positive number, 9.8 meters per second squared, times 0.6403 seconds squared. I got 37.99 meters. Okay, so after 0.6403 seconds, the dart has a coordinates of 50 meters in the x direction, that's how far it's gone, and 37.99 meters in the y direction. Last step. What's the height of the monkey at that time? The monkey's equation looks like this: h minus 1/2 gt squared. So that is 40 meters, minus 1/2 times 9.8 meters per second squared times 0.6403 seconds squared. And I plug in the numbers, I get 37.99 meters. So after this time, the dart has traveled 50 meters in the x direction and has a height of 37.99 meters. The monkey has dropped to a height of 37.99 meters. And so the dart and the monkey are at the same place, and the dart hits the monkey. So there we go. We were able to show that if you aim directly at the monkey, again, your dart and the monkey are both affected by gravity in the same way. And so if you aim directly at it, your dart will end up hitting the monkey. And if you don't believe me, again, you can watch a video. So there's a really nice video posted in the links and videos section of D2L. So I'm in the links and videos section again of D2L, and here's a nice video shoot the monkey demonstration on YouTube. And let's Let me show you what it looks like. Okay, you can see that that cannon is aimed right at the monkey. Now, when he launches it, there's an electromagnet which is going to drop the monkey at the same time, and boom, you can see it hits exactly right. By the way, this doesn't depend on the initial speed, so no matter what your initial speed, if you aim directly at the monkey, you will hit it. So this is a slower speed, and you can see how it happens there. So that's a lot of fun. So I hope you guys enjoyed this video and this example. There's a couple more things that I'm gonna just mention here. There are formulas for how far the projectile goes in the x direction and also its maximum height. And these formulas can be derived using the kinematics equations, and I'm just giving them here for your reference because these are actually useful. You can always go back to the kinematics equation and derive these, but it's kind of nice to know them, have them at the tips of your fingers. Just be careful. This last one for the range that it goes, r, this range, it only works if the 2 points here are the same height, the initial point and the final point. So if you're launching something off of a cliff, or if you're shooting something up to a higher height, you can't use this equation. So this equation is only valid if the starting and ending heights are the same. So just watch out for that. A couple of other tips which are kind of useful to know for solving problems. It's useful to look at the top of the trajectory. So if I look at the point at the top of this trajectory, the object has no y velocity at that point. So that makes the equation simpler. If I know that the y velocity at that point is 0, it's a convenient point to look at. The other thing that's nice to know about this is that the thing is symmetric. So in other words, if I find the time that it takes to go all the way up to the top of the trajectory, that's going to be equal to the time it takes to go down. Okay? So the time up is equal to the time down. And another thing that's interesting to know is that the speed at a given height is the same. So the speed at point here, when it has velocity v1, that speed will be the same as the speed here at point v2. Some of you may realize this from conservation of energy. The point started off with some kinetic energy. When it reaches this height, this certain height, it has gained some potential energy, and so it will have lost the same amount of kinetic energy. But even if you don't know that, you can show it from kinematics, but it's just a useful shortcut to know that the speed at a given height is the same. So at point, the blue point here, if I call it 1, and the blue point here, call it 2, the speeds of those two, of the object at those 2 points, are the same. Of course, the direction is different, but the speed is the same. Okay, so I'm just going to summarize now. I hope that you are familiar with the concepts of position, displacement, velocity, and acceleration, and understand how these all relate to each other. I hope you understand that the x and y equations are independent because gravity is only acting in the y direction, and it doesn't affect the x direction. And we've got these equations for constant acceleration. These three, so this is an equation for the x direction, position, velocity, and then the last one is an equation which doesn't have time in it, which is useful. And then we have another set of equations which I didn't write here for the y direction. So you have three equations for the x direction, three equations for the y direction, and we went through some examples of solving problems using those equations here. So I hope you've found this little cleanup lecture useful, and thanks again for your attention.